this is Calculus 12, Chapter 3.2. We're going to be looking at differentiability. In order for a function to be differentiable, it must be relatively smooth. So here are some examples of non-smoothness. This is a corner. This is a cusp. So if it's not a cusp, it's a corner. So a cusp has tangents. One is going to be positive infinity, and one is going to be negative infinity. Okay, so this one's going to negative infinity, this one's going to positive infinity. So they're vertical tangents. This one is a vertical tangent. But this is going to positive infinity and positive infinity. So they have the same signs. It could be negative infinity to negative infinity. These ones are two different vertical tangents, one going to positive, one going to negative. So if you have something like this, one vertical tangent and one non-vertical tangent, we'll call that a corner. Also, any discontinuity will make a function not differentiable. Here's the theorem. Differentiability implies continuity. If f has a derivative at x equals a, then f is continuous at x equals a. So how do we prove this? We want to show that the limit as x approaches a of f of x minus f of a equals 0. Another way of looking at this is limit x approaches a of f of x equals f of a. Okay, that implies continuity. So we want to show differentiability somewhere in this proof. So limit x approaches a, and we're going to multiply this by x minus a over x minus a. And when we have this, we're multiplying by 1. So we're not changing the expression. Now we reorder this. Limit x approaches a of x minus a. Multiply this by limit x approaches a f of x minus f of a over x minus a. If we substitute this in, a minus a is 0, and here we use the definition of this. This is f prime of a. So this is differentiability. So if we have differentiability, we have continuity. And our proof is done. Note, the converse is not always true. Okay, P implies Q. Q does not imply P. So if we have continuity, that does not imply differentiability. It's a different statement. And all we have to do is go back up to where we were. Here we have continuity. Here we have continuity. And we don't have differentiability. Here there's no continuity because this is a vertical tangent. This is a vertical tangent. This must mean that this is a vertical asymptote. Theorem 2, IVT for derivatives. That's intermediate value theorem for derivatives. If a and b are any two points in an interval on which f is differentiable, then the derivative f prime takes on every value between the derivative at a and the derivative at b. So what does this look like? Okay, here we have a point A. Here we have a point B. The slope at A is -1. The slope at B is 1. It's not quite to scale. It means that we get all the slopes between -1 and 1. So we get -0.5, -0.25, 0.3333, 0.75, all the way to 1. It's important to note that we don't necessarily get just these values. If I draw something like this, okay, we get a slope of -1. We get a slope of 1. Here, we have a slope of maybe -3. Here we have a slope of maybe 2. Okay, it doesn't exclude other values, but it tells us we must have values all the way from -1 to 1. Question 12. Let's do the derivative. Y prime equals 4/5 x to the power of -1 over 5. Okay, so I'm just using the power law. We can rewrite this as 4 over 5 times x to the power of 1/5. Okay, so we get 0 in the denominator. That must mean this is a cusp. It has a discontinuity, but it's a special discontinuity because we have a vertical tangent here and a vertical tangent here. So it's a cusp. You could show this with limits as well. Here, this looks like a vertical tangent. So let's rewrite h of x. So the derivative, so we have 1 over 3x minus 6 over 2 to the power of 3. Okay, so this is a vertical tangent. And we have a vertical asymptote, so it's not differentiable at x equals 2. Sorry, I made a mistake earlier. This is discontinuous as well. There's a vertical asymptote here. Okay, so the only one that is continuous is the corner. And that completes this lesson.